For the last part of problem 2, there are two questions really. The first is the problem gives 3 different processes, all of which are said to be irreversible. And the first part of the question is, why are they irreversible? What makes them irreversible? And then the second part of the question is, what can we do to make those irreversible processes into reversible processes? What's the equivalent reversible process? So for the first case, the process is the melting of ice in a room that's held at constant temperature of 298 K. So the ice is at 0 degrees C. The room is at 298 degrees C, or 298 K, 25 degrees C. And so obviously it's irreversible because the temperatures are not balanced. Remember that an irreversible process is any process that takes place with unbalanced forces, and a temperature is a thermodynamic force. A reversible process is one that takes place only with balanced forces. So here we've got unbalanced forces. T at 0 degrees C is less than T at 298. They aren't even close. And so this would be really 273 K, I guess. And so they're irreversible. How would I make them reversible? Well, I'd have to change the surroundings, right? The room here is the surroundings, to some sort of situation where the forces are balanced at all points, and that means I've got to make these surroundings, the room temperature, match the temperature of the ice at first, and then slowly increment the temperature of the surroundings upwards. So I got to start at 0 degrees C and then slowly increment the temperature upwards until I reach the final temperature that I want, which would be 298 K or 25 degrees C. All right, part number 2 is the same kind of situation, but instead of a melting process, it's a chemical process of sorts, a dissolving process. So I've got some sodium chloride solid dissolving into pure water. Is that reversible or irreversible? Well, the problem says it's irreversible. Why? Well, because the chemical potentials are not balanced, right? At equilibrium, that's what force balance means, right? That you're at equilibrium, or very near equilibrium. The chemical potentials in all regions have to be equal. In other words, the chemical potential of the salt in the solid phase has to equal the chemical potential in the solution phase. And if I've got pure water here, then obviously the salt in that pure water is not balanced. The chemical potential of that salt is not balanced with the chemical potential in the solid. So what I have to do in order to make this process reversible is I have to exchange the pure water with a nearly saturated solution of sodium chloride, and then slowly reduce the concentration of the sodium chloride to allow a little bit of sodium chloride to dissolve into the now almost saturated solution, but not quite saturated, and keep on doing that until I've dissolved enough of the sodium chloride to mimic the conditions of the original process. In the third case, it's very similar. I've got some acetic acid, again, in pure water, and that acetic acid is going to dissociate, right, as all acids do. But it hasn't started dissociating yet. It's pure water, so there's no H+, and there's no acetate ion. And so it's irreversible because the chemical potential of the overall reaction, right, the chemical potential on this side, on the reactant side, is not equal to the chemical potential on the product side at first. So it's an irreversible, unbalanced forces situation. In order to make it reversible, I've got to change this pure water again to include enough concentration of H+ and acetate ion to put this acetic acid essentially at equilibrium, right? I've got to have essentially equilibrium concentrations of these guys to start with, so that I'm not out of equilibrium with the acetic acid that's already in solution. And then I'm going to start lowering these concentrations bit by bit into allowing the acetic acid to dissociate the way it wants to, but doing so always essentially at equilibrium. All right, in all three cases, you can see it's basically the same thing. I have to adjust the conditions out in the surroundings in order to bring my system into essentially or very close to equilibrium with the surroundings, and then change conditions in the surroundings in order to sort of lead the system to the final state that I want. All right, that's the end of number 2. Next time we'll do number 3.